Welcome back. In this final video of week 7, I would like to show you a demonstration of the Metropolis-Hastings Markov chain Monte Carlo. We just saw what the algorithm was in the previous video. If you have not seen it, I request you to take a look at it, without which most of this will not make sense. Okay, so we are doing a parameter estimation, but now it is no longer an offline Bayesian as we had done in the previous videos, but it is actually a Metropolis-Hastings MHMCMC algorithm. Let me just put this Metropolis-Hastings Markov chain Monte Carlo. We are using the same problem as before. Now, this problem, I have just copied it from the previous video. So it says generate 11 samples of the heat flux, etc., but we are not going to do that. We are going to try to use this MHMCMC Bayesian approach instead of the offline sampling given above. Okay, so what we will try to do is we will give some initial guess. So here it is 900 to 1500. So we will just give one initial guess somewhere within this range. Let's say we give 900 and let's see how quickly it jumps in. Now remember, typically we need a burning sample. Typically we need a burn-in period. Okay, which we are ignoring now. Okay. So maybe we'll include it towards the end of this video just to see how that works. Okay, so now very simple. Initially, we have the same parameters as before, the same thermal conductivity, length of the slab, temperature, the same measurements, the same uncertainty in the measurements. Nothing really has changed. Now, all I am doing is giving some initial guess for Q. So let's give this as 900. And we give an initial guess for Q as 900. Now, remember, you now have a new proposal region. The proposal region means this. If you gave Q as 900, you want to now take the next point somewhere in the neighborhood of Q. And you are going to do that with a Gaussian. Okay. Now, as usual, our T simulation is just, this is our forward model. I should have written that a little bit more clearly. Forward model is this, which we got from physics of the problem. Once we come to machine learning, we'll see how to make this forward model if we don't know it through physics, and we can still combine it with something like MHMCMC. So that would be some interesting results that we look at a couple of weeks from once we come to machine learning. Okay, here is our MHMCMC algorithm, same as what we wrote last time. You first initialize Q, which we have done to 900, and then you calculate a next sample. I'm always taking a sample around the previous value of Q with a standard deviation of 90. I'm going to keep this constant. You can vary this if you want, but I'm going to keep this constant just for convenience. We calculate the new probability. We calculate the new old probability. If the ratio is greater than 1, that is, nu is more probable, we accept it. If nu is less probable, then we actually accept it with the ratio of P nu by P old. Simple idea. So the first step, let me actually make this into a clear step and call this step 1.1. Okay. This is just for your notes. As you go through this, hopefully this will make things a little bit clearer. We want to create some NS samples. Now, I have decided that I am creating only 11 samples. This might be too low a value because we are randomly sampling X. Here is where offline Bayesian might work well because we have already given some range and already somebody has decided a nice range. But as you will see, this will not do too badly. Okay, so you generate some NS samples. The idea is this. You start at the second sample and you generate the next sample in the Markov chain. Okay. So this next sample will be centered. So this is a Gaussian with mean as the previous Q and standard deviation as sigma P, which was in our case, this was 90. We have kept that as a standard. So this rand n that you see here simply means a normal random variable. This MATLAB automatically generates for you. Any other programming language you use also will generate it for you. It is there within standard libraries. There is a standard procedure to do so, which also looks remarkably like this A selection. This is called an acceptance rejection ratio, but I will not discuss that for now. For now, let's say we have a method of generating this normal random variable. So this is Q new is now a random variable with center at mu and a standard deviation of sigma p. Okay. Q old was the same as mu. In fact, let me just change the order of these statements so that it doesn't look. If you wish, we can call this Q old plus sigma p. Well, let me leave it as mu, just so that it is not confusing. I'll move this here, just playing around with a little bit of the notation, just so that when you read it, it's a little bit clear later on after the class. Okay, now here is my T simulation with the old Q. Okay, this is the error and sum of error square with old Q. So remember, we are actually comparing two different Qs, and we already have this accepted within the sample. We are now deciding, should we accept Q new or not? So for that, we calculate these. Now, some of you who are good programmers will know that the way I have programmed it is not efficient. But nonetheless, given the algorithm I have given above, and given that we are writing very simple codes, the lack of efficiency is not a big deal. I am just writing it in a way so that it is clear when you read it later. So this, of course, is AX plus B. I'll put brackets here just so that you guys can compare it with the formula that we wrote before. Okay. This bracket serves no purpose other than to separate out AX plus B. Okay. Same AX, same A, same B, except of course A is dependent on Q by K. So this is Q old by K, this is Q new by K. Same thing. This is T sim with the new Q. Okay. Similarly, error with new Q. All right. So P old is the numerator of the PDF Q new, and old, Q old, and P new is the numerator of the PDF Q new. Okay, we are only comparing numerators. Now notice this is e to the power minus half S old by sigma square. This is half S new by sigma square. This is sigma m corresponds to the measurement. So this is the error of the measurement. So it doesn't change. Regardless of whether I use a new Q or the old Q, the measurement doesn't depend on heat flux. Okay, or the error of the measurement, the uncertainty in the measurement doesn't depend on the heat flux. Now we had already decided that A is minimum of 1, P new by P old. Now, if it turns out that P new is higher, we will accept it. If it is lower, then we will accept it with probability. So now notice, U is a uniform random variable. This is just like throwing a toss with continuous values between 0 and 1. And in let's say A is 30% or A is 0.3. So in 30% of the cases, it will turn out that U is less than A. We will accept 30% of the value. So basically, we will accept these values with probability 0.3. Now, once I run through this entire process, what will happen at the end of this is, at this point, all the samples are generated. Okay. So what I will do is I will run the code till here. Okay. I'll run the code till here just to show you what happens. Okay. So when we come here, we can now write what the samples are. Okay, so you will see this samples. Let me write this again. The first sample was 900. The second sample was 1029.8, 1175.2. Now you can see slowly it is moving its way up here. Okay, so it has decided that these are the samples. Now let's see how well or how poorly these samples do. I took very few samples, but let's still plot the probability density function here and see what it looks like. Now, this process, this portion is exactly the same as the offline Bayesian. Now, remember, for the offline Bayesian, here is an offline Bayesian code. Of course, this was with A and B. But the offline Bayesian, all we did was we calculated these sums. P1 by sigma P1, sigma P2 by sigma P1, sigma P3 by sigma P1. All that is what we calculated with the given samples. Okay, it is just that the samples were pre-generated and kept as uniform. On the other hand, these samples were generated on the fly. We started randomly with 900 and we generated these samples. So as you see, the job of the Metropolis-Hastings is until here. Okay. This is end of MHMCMC sampling procedure. Okay. After it, it is simple evaluation. Okay, so let's call this step 4. Step 3, evaluation of the integrals. So our quantities of interest, what is the maximum a posteriori value, etc., is calculated at this point. Okay, now how do we calculate it? Same as before. We calculate P, you calculate P1, you calculate P2, you calculate P3. If you have a prior, you incorporate that also here. And then you calculate the PPDF. So if I continue, we can actually see what the probability density function looks like. There seems to be some issue here. Let me just check what the problem is. So if you run this program, you see this. Okay. So you can notice this. This was our initial sample, then a few samples here, and you see a nice probability distribution forming. Okay. You will see a nice probability distribution forming here. And you can see a little bit of the computation is waste, but at least after a few things, it has somehow zeroed in on the right region. Okay. Now what happens if we increase the number of samples, or if I change the initial guess to, let's say, 1200. Okay, so I could change the initial guess to 1200 and I could run it and we can see what happens here. You see it starts at 1200 and it goes all over the place. We can now look at what this looks like when we write QS. It started at 1200, went to 1236.9 and it just hovers around the same place. Notice that it is intelligent enough to just keep on hovering around the right place. It doesn't go off far away from where most of the probability is concentrated. In fact, I can also look at, let's say, what the value of QM is. It comes out to 1244.1, which is fairly close to what we had earlier. We can also look at the standard deviation, which is 11.7. So what this tells you is that the original probability distribution of this is has a within the sample sizes around 11.7. I can also increase the number of samples. Let's say instead of 11 samples, I put 501 samples. Okay. If I run it, what you will notice is that you see how many points are clustered right around the maximum. And it almost never takes points from outside this range. I can try this also with, let's say, an initial guess of 900. And you will see that from 900, 950, etc. Once it zeroed in here, it just stayed here. And it put a lot of points. Of course, I have kept from 1 to ns, I can keep a burn-in period of, let's say, B is, I had 500 points. So let's say I can take around 10 or 20. This is our burn-in period. And instead of taking the average from the first point, I can take from B plus 1. So I can go from here till there, and I can check what it looks like. So you'll see, oh, of course, I should have cleared everything till now. And we can rerun the entire thing so that it comes only from the beginning. Okay, so I made a mistake by plotting both of these together. Instead of doing that, we can plot in just from the burn-in period, and that will work just fine. So let's remove this. The point here is, even if you start at a bad initial guess, in fact, let me show you, you could have a really, really bad initial guess. You could even start on the higher end. Let us say we started at 1500, and we can see what it looks like. Okay, so if we started with a bad initial guess, 1500, it will work its way back and come to the right region again. And you can again check what QM is. QM is the mean Q. It turns out to be 1242. You see, it is remarkably stable, and this is the power of this MHMCMC algorithm. Regardless of how bad your initial guess was, even if you started right at the edge, again, I'll show you a very bad guess, and we can see how well this works. You can start with even 2000, which is well outside the range of where we guessed initially. You will see it starts with 2000, but it will quickly come back to the same range, and we can check what QM is, again 1242.9. So we always recover the same estimate for what a decent heat flux for this problem is. Of course, if we throw in a burn-in period, all these initial, 7, 8 initial guesses would actually have disappeared, and we would have been able to do the problem in a much more efficient fashion. So this burn-in period is an important thing in practical cases. For our problem, it's a simple one-parameter problem, so it doesn't matter there. The long and short of the MHMCMC process is, you start from some arbitrary initial condition, let's say 1200, and you can add as many samples as you want, and typically you will always converge to a decent value for the parameters. As I said, it is very efficient when you come to a large number of parameters. So it turns out that it is as efficient for large parameters as it is for small parameters. It's just that a pure Monte Carlo, a simple Monte Carlo, sort of the offline Bayesian, becomes lesser efficient as the number of dimensions increases. This doesn't care too much about the number of dimensions. So typically in the stock market, in large parameter problems, MHMCMC is used significantly. Now, what we will start in the next week is, everywhere here we were using our forward model from physics of the problem. Now, what happens if the physics is difficult or the physics is not known? In such cases, we use machine learning. So we will spend about 4 weeks looking at machine learning, and we will try to interface it with the methods that we have used so far within inverse problems. So I hope you enjoyed that portion. I will see you next week. Thank you.